so a couple reminders, and we're just going to put these officially into our notes. The limit of sine of quantity ax over x when x approaches 0, we just reconfirmed that that is equal to whatever a happens to be. So that is a constant, but it will change according to a. We also just kind of explored what cosine of ax minus 1 over x would be. And we saw in that situation, a had nothing to do with it, and that a was truly just 0. So those two things you'll need as we start working a little bit more with trig derivatives. The other thing that you're going to need to recall is something that you learned in Ham last year, or pre-calc, is what to do with the sine of a sum and the cosine of a sum. Yeah, Holiday?
Is that the sine, cosine, cosine, sine?
It is. It is. All right, so we call this, sometimes we call it the cheer. And what it is, it's not distributing, but it's the expansion of what you would do with sine and cosine. So yeah, in sine, it's going to go sine, cosine, cosine, sine. And then for the other half of it, then it becomes cosine, cosine, sine, sine, sine. So it's double cosine at the beginning, double sine at the end. And why do we say that extra third sine, sine, sine? Sign change. Okay, so instead of being a plus minus, I'm going to flip it upside down and call it a minus plus. It does not change for sine, it only changes for cosine. And then the order of the variables does preserve. It stays the same, so sine would still be of a first and cosine of b. And then a first and then sine of b. And then a first and b second, and a first and b second. So really the only other thing we got to watch for is that changing of the sign in the center. All right, so those are some reminders of things you've learned previously so that we can move on and do what the derivatives of trig functions are. All right, any questions so far? That's old stuff, but maybe just a refresher. All right, so this is our question of the day. What is the derivative of sine? All right, well, we don't have a power rule or a quotient rule or a product rule to help us out with this. So we have to go back to Newton and what Newton's rule is. So if you ever are unsure of a derivative, if you've ever forgotten a rule, you can always go back to Newton or Leibniz. We're going to do Newton in this case to help you figure out what that is. Okay, once we've proven it and we move forward in a day, then you don't have to keep proving it, just like we don't have to keep proving we've got the quotient rule and product rule now. But we're going to take Newton and we're going to approach it that way. All right, so Newton's proof. Newton's proof has a limit. Okay, remember what his is? You just did Leibniz. How does it go? Okay, f of x plus h, then what? Minus f of x all over h, as h is doing what? Okay. So we're going to do this with sine. The function is sine. So we're going to place f with sine. So this becomes the sine of x plus h minus the sine of x all over h. Now we have the sine of x plus h. That requires the cheer because it's the addition of x and h together. And so we would need to expand that using the cheer that we just reviewed. So this is going to go sine, cosine, cosine, sine. So it'll be sine first, cosine second with no sign change, and then cosine next and sine second, again with no sign change. So the x and the h fill in the spots there. And so that here is the expansion of what I'm going to put in yellow right there. But what else is still part of the numerator? Okay, I still have the minus sine x at the end, and I still have this over h. Okay, there are only two like terms in the whole numerator. Okay, if you look at the two cosines, they're different. One of the cosines is h, and one of the cosines is x. And if you look at how many signs are there altogether? How many separate little signs? There should be 3. Okay, I see 3 total in the numerator. All right, 2 of them match. Okay, which 2 are the same? Okay, the first and the last. So we want to regroup so that we can do factoring. And so we're going to reorder this. So we're going to keep the sine of x and the cosine of h first. But then we're going to put the minus sine of x second. And we'll end with the cosine of x sine of h. We do that so that you can factor. We often regroup things so that you can factor out what they have in common. And so now I'm going to look at, put a bracket around that. Those front 2 terms have a common value, and the common value they have is the sine of x. And so I'm going to factor that out. So I'll take that sine of x, and what will I be left with? Cosine of h minus 1. And then I still have the cosine of x and the sine of h at the bottom, and the whole thing is still over h. What I'm going to do now is split this up into common denominators. So I'm going to give the denominator h to both terms of this problem. It splits at the addition sign. It doesn't split around multiplication, it splits at the addition sign. So I will now have the limit as h approaches 0 of sine of x times the cos of h minus 1, and that will be over its own denominator h, plus, and then I'll have a new limit of the second half of the problem, and it will be, over its own denominator h. What's the variable here? What's the variable that's changing, that's approaching? H or x? H. H is the variable. So if x isn't a variable right now, x is a constant. And what can we do with every constant in a limit? Not get rid of it. Okay, if I had the number 3 or the number 7, what could I do with a constant thing that doesn't have a variable in it? I can move it where, Andrew? What do you mean? Say it louder. Okay, you pull constants out to the front of limits. That was one of the properties of limits we learned in chapter 2. So the sine of x has nothing to do with this limit because it doesn't have an h in it. I only need to have the stuff that had h in it. So I'll have cosine of h minus 1 over h. And in the other half of the problem, the part that is the constant is the cosine of x. And I'll pull that out in front of the remaining limit. So I'll be left with the sine of h over h. What's now in the brackets are the same 2 limits we started the lesson with. If you look back at the beginning, I'm going to shrink this down, way down. Okay, trace those back. We have cosine of h with a minus 1 over h. That is going to be connected all the way back to that value, because cosine of anything minus 1 over that same thing, and then the sine of h over h traces all the way back to that one, to the value of a. So we're going to replace them. So in other words, what am I replacing the cosine limit part with? 0. And what am I replacing the sine of h over h with? What's a in this case? 1. Okay, so I'm replacing those two values. All right, let's zoom back in so we can take a look at what we've got. So that gives me, well, I'd pulled the sine of x out front, and that's multiplied by 0, plus I'd pulled the cosine out front, and now that's multiplied by 1. So if the sine of x is multiplied by 0 and the cosine of x is multiplied by 1, what am I left with? Cosine of x. And what was our question? What question were we asking? What's the derivative of sine? And the answer to that question is cosine. Okay, the derivative of sine is cosine. We just proved it with Newton. In your homework, you'll be asked to do the opposite. You'll be asked to answer the question, what is the derivative of cosine? Okay, I'm going to tell you what the answer is to that, but you'll have to show the work to prove it in your homework. Okay, all right, so we're starting our collection here. We're going to make a little list. We're going to have the trig function and the trig derivative. How many trig functions are there? 6. Sine, cosine, tangent, cotangent, secant, cosecant. We're only going to do the first 2 today. Okay, so we've got the sine of x, and we're going to do the cosine of x. Well, we just answered the question, what is the derivative of sine? The derivative of sine is cosine. We just proved it. The derivative of cosine is not sine, but it is negative sine. And that's one of your homework questions, is to show that. And so you are going to copy almost line for line the Newton proof for cosine. The difference is, at the beginning, you start with cosine of x plus h minus cosine of x. And so your cheer will be cosine, cosine, sine, sine, sine. That will be your cheer. Other than that, you're going to follow the same reordering strategy, grouping, factoring, and then pulling out the constant. All right, but I'm going to tell you that the answer should work out to sine of x. Okay, so now we're going to practice some problems with that. Do you have to prove it every time? No. The only time you have to prove it is the one homework question where they ask you to prove it. Other than that, you just use that those are the values. Okay? Prove it once and then we're done. Okay, so let's practice. So this is going to all fall under the heading evaluate derivatives. Now, the product rule, the quotient rule, those all still apply. Okay? All right, so here's question A. If y is equal to x squared times sine of x, what rule will you need to find that derivative? Not power, product. Okay? Well, I guess a little bit of the power rule, but mostly the product rule. We're going to use the product rule to find the derivative, but we're also going to use the rule we know for x squared and the rule we know for sine of x now. So dy dx, when I write that, that doesn't mean you have to prove Leibniz. It just means that's the notation for derivative. And so we're going to do b a prime plus a b prime. So the b is sine of x. The a prime is 2x. Plus the a is the first part, that's x squared. And the b prime is the derivative of sine, which we just learned is cosine. And that's the derivative. That's the end of the problem. You could maybe write that a little bit nicer. Typically we would put the squared term in the front and then the 2x in front of the sine x. That would be probably the more traditional way to write that in terms of descending order, that you like to have the squared thing first. Okay, part B, or example B. Y equals sine of x over cosine of x. Well, let's find y prime for that. So what rule will I need for this one? I will need the quotient rule. And so the quotient rule says start with b and then do a prime, and then minus a and then do b prime, and put the whole thing over b squared. So we'll do that for this. We'll start with b. B is cosine. A prime is also cosine. Minus a is sine. And tell me again what b prime is? Negative sine of x. And that whole thing would be over the b squared. So what's cosine times cosine? Cosine times cosine is anything times itself. It's cosine squared. Okay. All right, what comes next? Plus sine squared. Ooh, anybody remember what cosine squared plus sine squared is? Good, that's the Pythagorean identity. Anybody remember what 1 over cosine squared is? Well, what's 1 over cosine? Secant. And so this is secant as our answer. By the way, at the beginning when I said sine over cosine, did that remind you of anything else? Okay, so what did we just answer the question of? We just solved, right, what's the derivative of tangent? We just did it. The derivative of tangent is secant squared, so you're getting a preview of tomorrow. All right, last question. All right, find the normal line to y equals cosine of x at x equals pi thirds. Well, as with any tangent and normal line, you first need to know the point, and then you'll need to know the slope. So my point is going to be pi thirds, and then whatever pi thirds is plugged into cosine, which is half. The slope is going to be the derivative of cosine, which is negative sine of x, which is the negative sine of pi thirds, which is negative rad 3 over 2. And so to finish, your normal line would use that point and the negative reciprocal of the slope. So y minus 1/2 equals, the normal would be positive 2 over rad 3, and then x minus pi thirds. And Terry, you do not have to distribute that and turn it into y equals mx plus b form. You can just leave it, okay? Because it gets ugly when you distribute, because you're going to have rad 3 on the bottom. So just leave it.